So we stopped the act for the tapered bar for video 2, right? And today we will be moving with the beam element, right? So for beam element, the displacements usually occur in the vertical direction and the rotations as well at a joint. So you have 2 degrees of freedom, and it does not mean that you are 3 degrees, third degree of freedom that in the axial direction is restrained, because you usually don't have axial loading in the beam, so that occurs in the frame element, right? So in the beam element you have transverse loading usually, right? But if you want, you can consider it as a frame element and solve this solve this method, right? So then the stiffness matrix will be different. For this is for a generic beam element. So I consider this beam, and what you can see is I have taken a representative beam element and noted the displacement in the vertical direction at that node is equal to v1, and the rotation is theta1, and displacement in the vertical direction is v2, and the rotation is in that location is theta2, right? So I have 4 unknown, so 4 displacements. And if you recall, your theta can be written if you know the value of your, let's say this is v. In that case, your theta can be written as dv over dx, right? dv over dx. Okay, so if your theta is dv over dx, right? So I have just written it, v is a function of x, right? If instead of v, I have written v as a function of x, right? So that's more generalized. So if you consider this beam, right? So let's consider this plane. So what Euler says is, if the beam is deformed, right, according to Euler assumption, so the plane section remains plane even after deformed shape, right? So you can see this at the neutral axis. It hasn't moved in longitudinal direction, but these points have now moved in longitudinal direction. It is even further when it is at the extreme fibers away from the neutral axis. So I'll call this deformation, the rotation is theta, and this angle will also be theta. Hence, this angle will also be theta. I'll take this triangle. Okay, this is the Z axis. So this Z axis, and I just exaggerate this triangle. Okay, so I need this displacement u, right? So u can be written at Z theta, right? So theta is, dv over dx, right? So you can write this as u, and the longitudinal strain, so it's in 1 dimension, right? So longitudinal strain you can directly write, if you know the longitudinal displacement, it's du over dx, right? So this is the strain. And you remember the bar element, right? The bar element, you only had 2 displacement and 2 degrees of freedom overall. Okay, so if you want to find u as a function of x, so you can only write it as a linear equation where you can substitute these u1 and u2, find a and b, and then you can write u as a function of, remember, n1 u1 and n2 u2, and you remember these are called the shape functions. Okay, these n1 and n2 are shape functions. Same principle here. You have 4 displacements. That means you can write a polynomial like this: ax cubed ex squared plus ex plus b with 4 constants, right? 4 constants you can find because you have 4 displacement, right? So that is exactly equals to the number of displacements. So here it's 2, that's why it is ax plus b. If it was 3, ax squared plus bx plus c. Since it is 4 here, ax cube plus bx squared plus cx plus d. And theta is dv over dx. You remember, right? So you can differentiate this and write 3ax squared plus 2bx plus c. So these are the two equations you have, right? It's the same equation. This is the first differential uh, equation of this one, right? So when x is equal to 0, in that bar element, I took x1 and x2 and defined the length as x2 minus x1. If that happens to be the case here, your simplification gets too complex, right? So I'll assume it's x equals 0 here and x equals L here. So it doesn't matter, length is then L minus 0, it's equal to L, right? When x is equals to 0, your V1, sorry, your V becomes V1 and these terms 0, 0, 0 and this becomes D. And when x is equal to 0, your dvx or dx, that theta becomes theta 1 and this term 0, 0, c. So that means two of your equations are already solved. You know c and d, right? And then only you need to find for a and b when x is equal to L, right? So you can find a and b, right? And after finding a and b, you can write an expression like this Vx. But this a, okay, but this a is a function of V1 theta 1, V2 theta 2, right? Similar to B, C, and D. Doesn't matter if it is theta 1 is C, we know that theta 1 is C, so that means V1 into 0, theta 1 plus V2 into 0 plus theta 2 into 0. It's equal to C, right? So any of these coefficients can be written in terms of these displacements. So we rearrange the term. So we need to express it in terms of not A, B, C, D. We need to in terms of theta 1, theta 2 and V1, V2. So you can write it again as like this. So it's called N1, V1, N2, theta 2, N2, theta 1, N3, V2 and N4, theta 2, right? So we call this shape functions as we defined earlier, right? In the bar problem, same principle, same concept. So I'm not going to simplify that here. So I have written these terms n1, n2, n3, and n4, right? So these are the shape functions to derived, and just for the case, so you can rewrite epsilon x is equal to du over dx, right? So you know, uh, this was so your u was, you remember what was u this term, right? Z dv over dx, right? You can take z out. Dx, so it's the second differential, okay? So that's going to be the second differential d2 squared e dx squared. right? Why we specifically take epsilon x? Because you can see, if you take this u, right, or the longitudinal strain, this u, within this u you have v, right? And that within v is compromised with all of these displacement, right? So v is a function of all of these four displacement. So if v is a function of all four displacement, then you know that u is a function of v, right? So that means again u is indirectly a function of these four displacement. So that means if you take this du over dx or whatever, that will be a function of all four displacements indirectly, right? So that means if you take the longitudinal strain, you have the relationship with all four displacements. That's why we take longitudinal strain. So that becomes a one-dimensional analysis, right? For this case, right? So you can write. So you remember the equation we derived that. So the stiffness and you remember the stiffness function we wrote. So this is for one element, right? So this is the volume integral of what? B t into t to p dv, right? So volume integral of this, right? So since this is a one-dimensional case, because you only have one strain component, right? So this becomes similar to bar, right? So one-dimensional problem. So that means your D matrix is essentially becomes Young's modulus, right? It's 1D, right? Because you only have longitudinal strain, and within the longitudinal strain, you have its relationship between those four displacements, two translation and two rotations, right? Okay, so you need to find what is this B, right? So you know that epsilon is B into D. We defined this in the first video, right? So that means how the displacement relates with this strain, right? How the displacement relates with this strain. So this is the strain, right? This is the displacement, how it is related uh, with this strain, with the displacement, right? How strain is related to displacement, and then we can see what is actually B, right? So this V is N1 V1, N2 V2, and N3. So you can write this B as this, right? So in matrix term, this is N1, N2, N3, N4. You can write like this, and it's into V1, theta 1, V2, theta 2, right? And you know what are these N1, N2, N2. So that is a function of X, right? So that is that can be differentiated using X, right, with respect to X. So you remember the this if you recall this, so you can write this d squared d over dx squared, right? If you recall this, right, you can write this expression. So it's d2v over dx squared into z, right? So you can write epsilon naught. So v1 is here, so you can, so this z is a term, so that's going to be z dv squared over dx squared, right? So you can write this as t n1 squared over dx squared d, sorry, this is not n1 squared, this is d squared n, right? So this is the first element of the matrix, and this is the second element of the matrix. And this is the third element of the matrix. X2, okay. Right, into this displacement, right, v1 theta 2, right? So once you differentiate n1 with respect to x 2 times, right, 2 times you have to differentiate, right? So that's going to be 6 x squared first, and then second it will be like this. So if you differentiate it 2 times, you will obtain this as minus 6 over L squared plus 12x cube, and this would be minus 4 over L plus 6 x over L squared. So this would be simple L, okay. So I wrote it simple L everywhere. So this would be okay. So from that you can obtain, if you know the displacement, the other term is exactly B. So that means you know what is the displacement. So this is the displacement matrix. This is D. So this whole term would be what? B, right? Okay. So it's bit long, but you can still do that. So you can write an expression for the strain energy, right? So, and the force, right? So you remember the stiffness was volume integral. So here, the longitudinal strain is not a constant along the cross section. So that means it should be integrated along the cross section as well. So we should first integrate it over the area, cross section area. Then you can integrate it from 0 to L, right? Should be area integral, because the longitudinal strain we are taking is not constant over the section. But if you recall, any of these points are same in vertical direction, right? Vertically, any of these points are having the same amount of v, right? Same amount of theta, right? But longitudinal strain is not, it is different, right? Can you see? It is different, right? It's 0 at the neutral axis. So you have to integrate that. So this is the volume integral. So you know this is B, right? So within B, you have some term like this. So B, I will write that B. You have to transpose it and write. So this is, you remember this is E, right? Why? It's one dimensional solving, because we only consider the longitudinal strain, right? Okay. dA and dx. So dA is the area, for area, dx is for L, right? So from this B, you can take a Z out, right? You can take a Z out. And you take the transpose. And you can take the E out of the equation as well. That's a constant. Right? So from this B as well, you can take a Z. And that's the same matrix, but not the transpose. dA dx. So what can you say about these three? Z into Z over dA. So if you recall your structural analysis, so this is Z squared dA, right? So what's that? The second moment of inertia I, right? Z. So I think you are familiar with y squared dA, right? So your section is defined in xy plane, so then it's y squared dA, right? So it's square dA, it's a square dA means again the section modulus, right? So not the section, so second moment of area, right? So you can take that integral as it is for instead of this integral. So this is the area integral, right? Z square dA. So you can take that EI as well, right? So EI as well. And you have to then 0 to L, these two, right? Into dx. So when you simplify this, you will obtain so when you simplify K, right? When you simplify K matrix, so you will obtain something like this, right? So this L, this is capital A or L, this is simple L, okay? So in your case, okay? So you can take that 1 over L cube out and write this expression. So this is for the, let's say, ith element, right? So single element, right? Element stiffness matrix. This is element stiffness matrix. So this order is really essential because this is V1, this is theta1, and this is V2, this is theta2. You have to remember that you can't interchange because we define this whole thing using this order, right? Even in the example problems as well, you have to take V1 theta1 and then V2 theta2, right? So V1 theta1, V2 theta2, right? So this is the V. So when you once you need to let me show you how to assemble that. Just imagine if you have some beam element like this, right? So I'll consider for the first part. So you have, this is the first node, right? So yeah, you have E1 and theta1 and theta2, and here V3 theta3. So I'll just write these three. Okay, so for the first element I can write the stiffness as this. So something, so EIOL squared is common, right? You have to keep the common term out of the matrix, otherwise you can't easily simplify. Or else the best thing is to put this into inside, so then it will be something like this matrix. So I'll say this is how to write notation. I will call x1, x2, x3, x4, right? X5, x6, x7, x8. X9, x10, 11 and x12, x13 and x16, right? And I will call this for the second element, it will be like this. So this is the value of the stiffness matrix. Okay, I will call this y1, y2, 3, y4, and the final value is y16. Okay, so this is related to I need to write this somewhere here. The fourth row, fourth column. Okay, so this is related to v1 theta1 and this is v2 theta2. Okay, and this is v1 row, v2 theta 1, v2, theta 2. This is going to be, so this is connected between v2 theta 2 and v3 theta 3. So that means second node and third node, right? So this is v2. That order is very important. Theta 2, v3, theta 3. So this is going to be v2. So the second row will be theta 2. This is v3, third row. This is theta 3, the final row. Right? When you assemble it, so you need to consider, you need to write like this. So I'll just consider this is two element. Okay, so I will erase this part. And here, these are the element stiffness matrix, right? For the element 1. This is the element stiffness matrix for element 2. For element 1. For this is the global. For global, you will have 6 displacements, right? v1 theta 1, v2 theta 2, v3 theta 3. So that means 6 by 6 matrix. v1 theta 1, v2 theta 2, v3 theta 3, v1 theta 1, v2 theta 2, v3 theta 3, right? So how to find this is, so this is very easy. Make everything 0 first, right? Make everything 0 first. Everything is 0. Okay. And for the first element, you need v1 row, v1 column, right? So you need what's in v1 row and v1 column, right? So from this element you can write, so here no v1 in this element, so you only need this v1 row, v1 element, so that's mean x1, right? So when that crosses at x1, so this is going to be x1, right? This is v1 theta 1. Again, v1 theta 1 means here, right? x2, right? x2. Then v1 v2, v1 theta 2. v1, because v1 is not in there, so we can without no worries we can use this same element matrix, v1 v2, v1 theta 2, x3 and x4, right? x4. This is theta 1, right? Theta 1 is also not in this matrix, so theta 1 is here, theta 1 v1, so theta 1 theta 1, theta 1 v2, theta 1 theta 2. So you can without no worries write that same thing, right? It's the same. If you need theta 1 v1 element, so you need to go to, so where is theta 1? So theta 1 is not here, theta 1 is here, v1 element is x5, right? So since theta 1 is not in that matrix as well, you can write x5, 6, 7, and x8. Right. Similarly, you can write theta 3 and v3, right? So theta 3 and v3 is not in the first matrix. So theta 3, v2, theta 3, theta 2, theta 3, v3, theta 3, theta 1. So you can see this element is v1 v3, right? v1 v3, v1 row, v1 v3 column, but there's no such element because v1 and v3 is not in the same matrix. Those are not connected, 1 and 3, right? So that's why it is 0. That's why I told you keep everything 0 first, then write the values, right? So the not irrelevant things will be 0 at the end. So for theta 3 and v3, you can, without any hesitation, you can write these terms, right? Theta 3 and v3, because theta 3 v3 is not in this matrix. So theta 3 and v2 will be y11, right? This is y12, sorry, y13, y14, y15, and y16, right? This is y13, y14, y15, and y16. This is y9, y10, y11, y12. So theta 1, theta 2, v3. Sorry, theta 2, theta 3. Theta 2, theta 3. That's going to be y8, right? Theta 2, v3. That's going to be y7. There's no theta 2, v3 and theta 3 here, okay? So you can, without any problem, right? So, and the same thing you can write here as well. This is my, it's going to be x7. This is going to be, I think, 9 and 10, right? Okay, so this is the problem, v2 theta 2 and v2 theta 2, because these elements are connected at that point. If you recall, as you can see, v2 theta 2 is here, and as well as v2 theta 2 is here. So in that case, you have to just add those values, right? That's it. v2 theta 2 and v2 theta 2. So here it will be x12 plus y2, right? So here v2 theta 2. So this is very easy. You just need to multiply these, sorry, add these values, right? So I'll show you the pattern. So this is going to be x12 plus y2. This is going to be x16 plus y6. This is going to be x11 plus y1. This is going to be x15 plus y5. So you can see what actually has happened is you overlap some rows and columns. So y1, y2, y5 and y6. You can see this is the element stiffness matrix for element 2 and this is the element stiffness matrix for element 1. You have added overlapped at the common location, right? V2 theta 2. So this is your global stiffness matrix, right? Global stiffness matrix. So with that you can define everything, right? So if you write the force equation, so you know force is equal to stiffness into displacement. So you know the for this is for the global structure, right? So in the global structure, if you know the forces, so we don't know the what are the forces, okay? So I'll write. So again that same order, F1. So vertical displacement corresponds to F1 for the linear force, right? Then theta 1. So this is V1. For theta 1, it should be M1, right? Then V2 theta 2. V2 for V2 you can write F2. Then theta for theta 2 you can write M2. So V3 you can write F3 and for theta 3 you can write M3 that corresponds to theta 3, right? So this is your stiffness matrix 6 by 6, right? And this will be your displacement matrix. So that's going to be V1 theta 1, V2 theta 2, V3 and theta 3, right? So thank you very much. We will do an example using this method quickly.